Hello everyone and welcome back to another video. Today we'll be taking a look at a British Informatics Olympiad question, and we'll be taking a look at the 2022 paper and the third question from it. So let's have a quick look at the question. I'll let you give a quick read of the question before I then jump to the solution. Here it is on the screen. And yeah, so now let's jump to the whiteboard and explain what I understand from the question, as well as the solution. So pretty much we have a certain CABD, which is pretty much the order in which the cars arrived or parked on the street. So this means that the first car, car A, parked in position 2, the second car, car B, parked in position 3, third car 1, fourth car in the final position. So we want to, this basically gives us various different possible preference lists, i.e. preference lists being the preferred spot in which each person, each driver wishes to park. So for example, in this one, the first driver could have chosen to park in position 2, thirded 3, seconded 3, thirded 1, and fourthed 4. Or it could have been all the same except the fourth one chooses to park in position 3, however, since that one's full, they have to park in position 4 anyway. So as I'm sure you'll see, that there are various different possible combinations which we can have, and we need to print the nth such combination. So let's just generate all the possible combinations first. So if we have like 4 blocks, each of these 4 blocks represent the possible preference lists which the ith driver has, where I is the block number. So let's say the first driver could have any of the possible preferences within this block, the second would have any of the possible preferences within the second block, etc. So consider the first driver for now. So this driver basically parked in position 2. When the driver got there, there was nothing on the street. So this is basically the situation when the driver got there. And now, since he parked in position 2, he or she parked in position 2, that means that position 2 must have been their preferred spot to park in. And now, this is basically the condition of the street once driver B gets there. Driver B notices that only the second position is full, every other position is free. So now, if we think that, if we consider the case when driver B has the first one as their preference, then that means that they would just park here. But then they clearly don't park here since C parks there. So that means that they could have had the third one as their preference, and therefore they would directly park there. Or they could also have the second one as their preference. However, since that one's full, they have to park on the next available one, which is the third one. So we can either have the second one or the third one as preferences for B. Okay, and now B's over here, and now we jump to C. So since C parked in position 1, that means that position 1 has to be the preference of C. Since if any other position was the preference, if this was the preference, this or this, all 3 of those would lead into it parking in the 4th position. However, it parks in the 1st position, therefore the preference of C must have been only the first one. Okay? So therefore we write 1 over here. And now for D could have had the first one as their preference, the second one as their preference, the third one as their preference, or the 4th one. All of these would result in the final one being the position where they park in, since everything is full, and then you would go to the next available one. So therefore, D could have had 1, 2, 3, or 4, any of these. And now, now that we've generated all possible permutations, all possible areas basically in which each of the people could have parked in, we need to generate what the 5th one is, or in general what the nth one is. Okay. Now, the way in which we're going to do this is because in each of these possible cases, you could go from 2, and then from 2, you can pick either one of 2 or 3. And then from 3, you can pick 1, and then from 1, you can pick any of them. Pretty much you can have any choice, you can choose one from each of these, and then that's how many choices you have. So in the first one you have exactly one choice. The second one you have exactly two choices, exactly one choice, and exactly four choices. If we multiply all of these, this gives us the total number of choices which the particular people have, which is 8 possible preference lists which could arise. Now, you might be thinking, well, okay, now we have 8 different preference lists, but how does this actually help us generate what the 5th possible preference list is? So that's what we will cover right now. So if we consider what are the number of preference lists which start with a 2, this particular 2. This isn't a trick question, it's basically all of them, right? Since the 2 has to be the first one, so all of the preference lists must start with the 2, okay? So now if we think, what are the number of preference lists which start with either a 2 or a 3 over here? Okay, so the number of preference lists which start with a 2 from here would basically be 4, since we have 4 different choices for these 2, hence it would be 4 different ones starting with 2, and another 4 starting with 3, since we also have 4 starting over there. Okay? Now, now let's formalize this a bit. If we start with 1, then there are 4 different options which we have. We can have any of these 4 over here. Okay? But now, now we need to formalize this, since we're just using like intuition here, but we need to use code, obviously. So, for the ith layer, the number of choices which each of the particular spots inside the ith layer has would be the number of permutations in the ith plus 1th layer. Okay. So what does this actually mean? So let's just consider the this particular layer, the one which has 2 and 3. So for each of 2 and 3, we have n choices, where n is the number of permutations of these particular things. The number of permutations would be, we have to start with 1, and then from there we can go to 2, 3, 4. So it would basically be 4. That would be the number starting with that would be the number of choices for each of the ones in 2 and 3. And then likewise with 1. So we can go starting with 1, we can end with 1, 2, 3, or 4. So we would have 4 choices. And now for 1, 2, 3, and 4, we have nothing after that. So that would basically just be 1 choice for each of them, since that is the only possible case which we have for all of them. So that's pretty much it. And the way which we'll compute these is we'll have to go backwards. So the number of choices of each of these is 4, since that's the number of elements. For our final one, remember each of them only corresponds to one more final choice, so they would basically just be 4. Now for each of these, it would also be 4, since we can pick any of the ones in the subsequent layer. So it would be 4 over here. Now for each of these, again, it will also be 4. The reason why it will be 4 is because we have to pick 1, and from 1 we can pick any of these. Okay? So it would be 4 over here. Now in this particular layer, it would be 4 if we choose 2, another 4 if we choose 3. So then 4 times 2, since 2 is the number of choices which we have, so it would be 8 number of choices which we have over here. Now how this helps in generating the 5th possible one is that if we know that we have 8 possible choices starting with 2, and then therefore we know that 4 of them must be from 2, and the other 4 must be from this particular 3. Hence the 1st, 2nd, 3rd, and 4th would be starting from this 2, 5th, 6th, 7th, and 8th start from the 3. So then we know that we have to go to the 3. Now from the 3 we know that the 5th, 6th, 7th, 8th all start from 1, so then we have to choose 1. And now from 1 we know that the 5th one is 1, 6th one is 2, 7th one is 3, and the 8th one is 4. We want the 5th one, hence we would choose 1. So our final one would basically become 2, 3, 1, 1. And then this in the format which they want is B, since B is 2, C, A, A. This is the 7th possible preference list. If we go back to the question, this is exactly what the output requires. So now all we need to do, if you understood this, good job, you're like 95% of the way there. We just need to translate this to code. So now let's have a quick look at the program, which I used to solve this. So pretty much, we start with just taking the inverse, this is the trivial step, and we have this pref array. I'll come back to what this does a bit later. But now this particular code just generates all the possible choices which each of the people could have had. So the way in which we do this is that if we remember, let's just go back to the whiteboard real quick. So if we remember, the choice for anyone could have basically been like if we cast our mind back to the choices when we're computing B, it was so B could have had their particular final parking element as their preference. They could have had the previous one if it was occupied. Now this is the key, because if it wasn't occupied, then they would park there. But then if it was occupied, they could have had that one. And now let's just consider that this one is occupied by any x. So B could have also had this one as their preference, since all of these would result in this being their parking place. So we just need to translate that to code. What we have over here is for I in range len, we iterate through all possible ones. Letter, lowercase letter, is basically 97 plus I. This is the lowercase ASCII value for the lowercase letters. And what we do is we iterate through each possible character. This is iterating through each possible lowercase character, i.e. each possible number, A, B, C, and D. And now we iterate through each of the parking placements. Now, if char is equal to the letter, then we basically need to append that particular letter to our prev array. Otherwise, if the char is less than the letter, then we also do this. And now if char is equal to the letter, then we know that we've basically reached the final place in which B could have parked. So then we break. If char is less than letter, then we basically continue appending. However, this is the key bit. If char is basically greater than letter, then we basically clear the array. This means that if we go back to the whiteboard, this means that there is a position free which B could have parked. Therefore, they wouldn't have parked there if that was their particular preference one. Therefore, it couldn't have been their preference one. Therefore, we have to clear all possible preferences which they could have had before that. Okay, and now we repeat this for all possible characters, and we append them into pref, where pref is prefix. This basically stores all possible preferences which each of the characters could have had in a 2D array. Okay, and now that particular code is done, and now we just need to generate all possible combinations at each of the depths. Okay, so we iterate backwards, remember. The reason for this is because the number of possible combinations which are in the ith layer would be the number of combinations in each of the ith plus 1 layer added together. So if you remember, if we go back to the whiteboard, then the number of combinations when we had I'll just redraw this a bit more neatly. So the number of combinations for each of 2 and 3 were the number of combinations which there were for 1, and the number of combinations which there were for 1 was the sum of the number of combinations which there were for each of these, 1, 2, 3, and 4, which are all just 1, but we add 1 4 times, so it's 4 times 1, where 4 is the number of layers at the ith plus 1 layer. And then we get this, that becomes the number of combinations for 1. Now the number of combinations for 2 is the number of elements inside this layer, which is just 1, times the number of combinations for this, which is 1 times 4. Hence that will generate 4. And now for 2 it would be 2, and then for each of these 2 we can have 4 possible combinations. So it would be 8, 2 times 4. This is exactly what we just implemented inside the code. So we iterate backwards, and now what we do is basically the step equals step times the length of the previous element, the pref. So what this does is for the next iteration, we have our step as the blocks in which we can basically choose from. And now we set previous to 0, obviously, since previous is basically the number of previous choices which we had, which is initialized to 0. And then we increment it with step, where step is the number of choices which we had in the subsequent one. And now we just set AI to equal previous, since that means that AI would be the number which is in the previous thing. And then after we do this, what we basically do is, and now we've generated all possible things for the particular choices which we had in each layer. What we do is we iterate through each possible array, And now, if the number of choices which we have is greater than our current counter, then we, if it's greater, then we subtract off item from I, since we want to go down a bit. For example, let's say we have 4 choices ranging from 4 to 8, and then we want the 6th possible one. So then the current I value would be 4 plus 4 would be 8, but then we don't want 8, what we want is 4, since that's the least possible value in which that I could have. So we subtract off I, and then we basically concatenate this to out, and then we break, and then we just repeat. So we break out of this for loop, but then we repeat for the next item, and that's how we generate each of the possible elements. And that's pretty much it. Then we just repeat this, and then we print the outputs. And now, this was a bit of a confusing code. If you would like to have a look and play around with this, feel free to check out my GitHub. I have all of these inside the GitHub. So now, let's just test this on a few strings inside the mark scheme. So let's just go here. No, maybe let's do a bigger one. Let's go here. Oh, sorry, I'm actually running the 2021 one. So, okay, let's just run the correct one first of all. Okay, now let's see if our code works. It outputs this. Now if we go back to the mark scheme, we can see that that is exactly correct. Now let's test on maybe the final one inside the mark scheme. Over here. Now let's go here, and again it outputs this, which if we go back to the question, is exactly correct. So yeah, that's pretty much it for this particular video. I really hope you enjoyed watching. Hopefully you learned something new about the way in which you generate these recursive functions. They are a repeating pattern in the BIR petition for Informatics Olympiad. So yeah, if you enjoyed, please be sure to leave a like and subscribe, and check out my GitHub as well if you want to look at the codes in more detail and play around with them a bit more. And thank you for watching. I hope to see you in another video next time. Bye.